Okay, so we're starting again from where we left it. This lecture in the last part. In the last part, we saw a couple of items. First was a general motivation of what optimization problems look like and where they arise. And then we started looking at different formulations alongside with some applications to motivate them. So the first formulation we looked at was the optimal control problem, and the motivating example was a tubular reactor with a bifunctional catalyst. And then the other one, the other formulation we looked at was, or type of class of problems, was bi-level optimization problem, BLP. And the motivating example was the manipulation of microorganisms using modeling approaches to overproduce desired products. Today we're continuing with the theme of formulations or general classes of problems that are addressed by optimization formulations. And the first problem we're going to see today is on stochastic optimization problems, either SP or SOP, stochastic optimization problem. And it's basically dealing with optimizing systems subject to uncertainty. In chemical engineering processes and models, we have, generally speaking, three types of uncertainty or sources of uncertainty. We may have input variability, we may have disturbances, and we may have parametric uncertainty, which is the bigger class, I think, of problems we have to deal with. For example, when you're designing a plant, you don't know exactly the kinetics, you don't know exactly all the physical properties, and therefore you would like to be able to gauge the impact they have on your investment and on the processing ability or operability of what you will end up designing and implementing. So if you consider uncertainty within your modeling, then it results in designs that select decision or design variables so as to optimize the expectation of the objective function value or the objective index. You don't have a single value because now your parameters are stochastic variables, the random variables, and therefore you expect a distribution of values of the objective to actually be the result of this. And you may have to soften up constraints of qualitative nature into either probability of satisfaction of those constraints or satisfaction of their average value. The above ingredients may be all present or in part in resulting formulations. So let's look at some stochastic programming formulations. You have, as usual, your decision variables x, n in number, and x in number, and you may have your uncertain parameters, which are random variables psi, distributed according to a joint probability density function. The PDF may be continuous or discrete, accordingly also the big set psi to which the random variables belong to. So the main formulation is as follows. We want to minimize a performance index, f hat, which is the expected value of your actual performance index with respect to x. And it's subject to the usual equality and inequality constraints we had before. The only difference here is that they have extra arguments, which are the random variables, the parameters of the model. So focusing on feasibility of the inequality constraints and regarding the model equalities as hard constraints here, a choice of decision variables may not satisfy them for all realizations of the uncertain parameters. So basically, if you choose an x, some of your inequalities may not be satisfied. So what do? We need to define a looser type of feasibility in order to be able to derive some solutions that we can apply in practice. So the first type of relaxation is that we do to inequalities what we did to the objective function. We take its expected value, that's the mean value of the constraint with respect to the parameters xi, and we say that this mean value should be less or equal to 0, whereas in reality we wanted all g to be less or equal to 0. So that means that some of these constraints, possible combinations of x and xi, will result in infeasible constraints with this. Then the second type of relaxation is the probability of satisfaction of the constraint, or this has another name, which is called chance constraints. Basically what you do is you say that the probability of the inequality constraint to be less than 0, I want it to be greater than some minimum probability epsilon. So this could be 0.95 or even tighter 0.99% of the time. Again, this means, though they may have some realizations for the random variables xi that are not feasible, but at least you know the probability of that happening. For example, safety constraints could fall into this type of formulation where you put a tight probability of them not happening, not being feasible. So how do we solve these problems? Well, the solution of general stochastic programming problems is often either based on discrete samples, so we create scenarios where we sample from the PDF several scenarios of the values of the randomly distributed variables, parameters xi, and we create instances which we solve simultaneously, use quadrature forms for integral evaluations. I talked about the multiple scenarios, and basically what you're trying to do at the end of the day is to transform the problem into something that you can solve with conventional solvers, such as nonlinear programming solvers, and therefore you reformulate with whatever technique you use your problem into a standard nonlinear programming problem, and you try to solve that in that way.
I've got a question.
Yes.
Can you go 2 slides? Yeah, that one. Once you apply the second relaxation.
This one, yes.
Yeah,
yeah.
I think the first relaxation is implied. Say epsilon to be 0.99. Then
it depends on your epsilon.
Okay. Okay.
I suppose.
So this means that if you have a large enough epsilon, say more than 0.5, then
yeah.
First relaxation is included in the second one. Or do we explicitly need first and second one to have a...
You wouldn't use both, I think. Not entirely sure what happens in this case. I haven't thought about it.
Okay.
But yeah. So moving on to this case, this is not a case. This is actually a summary of all the formulations we've seen so far. So what we talked about and what optimization can do is, or how you can do it, is encapsulated in this picture. So in terms of variables, you may have continuous variables, integer, or binary, and you may have control functions as arguments to what you are trying to extract or design with an optimization problem. In terms of parameters, we may have the case of what we just saw, which is uncertain parameters. And the formulations are these types, which we've just looked at. So you have the mathematical programming general formulation, which can be classed into nonlinear programming, mixed integer programming when you have integer variables, multi-objective optimization, bi-level programming when you have one optimization problem nested into another, stochastic programming, which we just looked at, and finally, optimal control problems. So these are general classes of models and problems and formulations, some of which might be part of another one. So for example, the second level optimization problem here in a bi-level, it could be a mixed integer problem, whereas the top level might be continuous or vice versa. So these are the formulations nonetheless, and what we strive to do with these formulations is somehow reformulate them so that they can be addressed with the existing types of solvers, which are only two types. One is continuous variables, and the other one is solvers which are able to deal with mixed continuous integer variables. So this is more or less a sketch of all the types of ingredients an optimization problem can have, all the formulations you can have, and how you go about to solve them. Are there any questions before we move on to the next phase, which is to look, I think, at algorithms? Okay, so I'm going to discuss now not every type of algorithm that exists, but I'm going to discuss some of the important modern algorithms that came about in the last century and are being developed further in the 2000s. So there are basically three types of algorithms associated with all applications shown thus far, and with others that will be highlighted later in this section. So the important algorithms to solve these optimization problems of the previous slide is either linear programming or nonlinear programming problem solvers, solvers designed to address mixed integer continuous problems, and finally algorithms designed to give us deterministically the global optimum of an optimization problem which may not be convex and therefore has multiple minima. And these are the things we're going to look at. So the first type of method I will present as within this section is what are called interior point methods for linear programming and nonlinear programming. These are the most important problems first addressed by optimization methods were linear programming problems. LPs have the following properties. They have a convex feasible region defined by linear affine constraints and bounds if the constraints are not conflicting, and therefore you have a non-empty feasible region. The optimal point occurs at an extreme point of the feasible region, i.e. a vertex, because of the linearity of the constraints, and there is only a single global optimum to such a problem. So a general LP problem is formulated like this. C is a vector of constant coefficients which go into your objective function. X, I are your continuous variables that you want to choose optimally, and they're subject to linear inequality constraints and bounds, non-negativity bounds. This is a simple formulation, but general enough to demonstrate what I'm trying to show. So the person who is recognized to have invented the first solution methodology for linear programming was George Danzig, who invented the Simplex Algorithm for linear programming. Of course, there is a claim, and people tend to believe this is true, that Kantorovich in the 1930s or 37 invented, well, he worked on linear programming, definitely, but he invented a solution technique which was held secret then by the Soviet Union, and then was later used to minimize losses in their army and maximize losses to the enemy. But nonetheless, the father of linear programming is considered to be George Dantzig with his simplex algorithm. The simplex algorithm is very, very simple to understand. You want to find a way to identify vertices by elimination operations among the constraints. Evaluate the objective function value at a vertex. Find a way to identify adjacent vertices from where you are. Evaluate a measure of how much each of these adjacent vertices would improve the objective function, and move to the one that improves the objective, any one that improves it. Go to step number 2, which is evaluate the objective, until no improving vertices can be found, at which point you have a proof of the optimal solution. It's the global solution. So this is how it works. You start from here. This is the feasible region. In general terms, is called a polytope in higher dimensions, which is a multidimensional polyhedron. So the solutions we know are to be found on some vertex. So you start at a vertex, provided you identify one. You move to the one that improves the objective, any one around it, and you follow the path until you are at a point where, to improve the objective, you would have to leave the feasible space. That's the last vertex, which the hyperplanes of the objective function are in contact with. So this is the way we minimize the function, and therefore up there is the optimal solution, and you stop because you can't find any vertex that improves it. So if we go to see what was published about various algorithms of the 20th century, this is Science News, Society of Industrial and Applied Mathematics publication. Among the top 10 algorithms, best algorithms of the 20th century, is George Dantzig's simplex method for linear programming. It is interesting to read what it says. It says here that it's one of the most successful of all time because linear programming dominates the world of industry, where economic survival depends on the ability to optimize within budgetary and other constraints. So that's the motivation behind it and why it's very important. Now, there was a big question in linear programming. Are there any polynomial time algorithms to solve the problem? Polynomial time means that, let's say, in terms of the number of variables, if n is the number of variables, is there a low enough exponent k which typifies how many iterations the algorithm will need to converge? The worst case scenario for the simplex algorithm with constructed examples is known to take exponential time, not really O2 to the n. This is an example of what I mean by exponential. It's combinatorial nature in the number of variables and constraints. And there is no known bound for the simplex algorithm. It can perform very badly, although in practice it doesn't do so for fairly large size problems. Some methods were found that would operate in polynomial time, but k was very large. And that was until 1979. And then in 1984, the following happened. It was the polynomial time revolution. It's due to another Russian mathematician, Leonid Kakian, who died very early in his life in 2005, who invented the ellipsoid algorithm. And again, this is from Rutgers, and it was the obituary, the announcement of the death of Kakian, who proved the existence of an efficient way to solve linear programming problems thought to be intractable up to that point. Again, I repeat, the simplex algorithm in practice performs really well, but the worst case scenario is exponential time. So moving on from this, another thing happened. In 1984, the proof of the ellipsoids by Kakian just proved that there should be algorithms, there was at least one way to solving polynomial time linear programming problems. But there was no efficient algorithm up to that time. This happened in 1984 by Karmarkar's method, which was polynomial time for linear programming, and it was called an affine scaling algorithm. And it even made the news in the New York Times. He, at the time, he was 28 years old. It says here, mathematician at AT&T and Bell Laboratories, and made a startling theoretical breakthrough in coming up with such an algorithm. Now, this affine scaling algorithm is more geometrically inspired, I would say. But and then following this, AT&T created a patent, and software and hardware was developed to be sold together to solve large-scale linear programming problems. The algorithm was original and theoretically sound, but there was even more to follow. So it seemed like there was a little avalanche around the early 80s happening in this area. So and you can see for how much they were marketing their solver, for $8.9 million at the time. And this is from the Wall Street Journal. Then came this paper by Gill, Murray, Saunders, and Tomlin, and Margaret Wright, where they showed, this was a seminal paper, where they showed equivalence, basically, of Karmarkar's method to a class of problems that was already known from the 1950s. And we'll see what it was. It initiated the interior point barrier method revolution, both for linear programming and nonlinear programming, in 1986. So, effectively, they showed that Karmarkar's method was equivalent to employing an old technique from nonlinear programming from the 1960s, which is to use logarithms to absorb the inequality constraints into the objective function, penalize them, and then solve this problem with more advanced numerical method, linear algebra techniques. The ideas are published fully in 1968, but the connection was not made, and the polynomial time complexity was not known until all this was connected together in 1986. So the barrier transformation of an inequality constraint problem into a sequence of unconstrained problems follows this logic. Let's say we have an objective function f of x, and we have inequalities gi greater than 0. The way we turn it into an unconstrained problem is by using a barrier parameter mu, and summing up all the logarithms of the inequality constraints, which have to be strictly feasible. Otherwise, you wouldn't be able to plug in here a negative number into the logarithm. So this reformulates the constrained problem into an unconstrained one. So the algorithm starts from a large value of the barrier parameter mu, where the problem does not really feel the influence of the objective. It's a big value of mu penalizes heavily the constraints. Minimize the unconstrained barrier objective function, not with standard unconstrained algorithms, but with suitably tailored routines. Reduce your mu, and small values of mu decrease the influence of the constraint, and this only becomes important when close to the boundary. So when you're close to the boundary, the logarithm becomes very, very large, repelling you to go inside. And minimize the barrier objective, starting from the previous minimizer, and go to step 3, where you reduce your mu until you're sufficiently close to a constraint minimum. And let's see an example later. Now, the issues were that log barrier methods only managed to solve small problems in the 60s and 70s, and they were abandoned basically from then on because of the severe ill conditioning as mu becomes very small. They used standard optimization methods for the unconstrained problems, which was the mistake or the problem, and they converged the unconstrained problems completely, which also required extra effort. These were eventually abandoned as new methods emerged for nonlinear programming, sequential quadratic programming, for example, and Simplex was the only viable method for linear programming up to that point. Yes?
Can I ask a question?
Yes.
Oh, brilliant. So does the use of the logarithmic barrier function in this case guarantee that you end up with an objective function which is convex over the area that you're...
No, your constraints have to be convex and your objective has to be convex.
Oh, right, okay.
So if you start from a convex programming problem,
yeah.
the logarithmic transformation is convex and it will preserve it, and you will have only a unique minimum. Okay. But if you start from G, the inequality is not being convex, or the objective not being convex, then you could have problems.
All right, but if you start with both of those things being convex, which is the case in lots of the problems that we solve in practice, then the barrier function guarantees that you have a function which is convex.
Yeah. And in fact, it preserves it for linear programming.